Welcome to the Materials Project website walkthrough. My name is Donnie Winston, part of the Materials Project team, and I'll be giving you an overview of how to use the website. The first thing to do, we find ourselves on the home page, is to go to the upper right and log in, or go to this button and sign in or register. Here I'm going to use my social login, Google account, to log in. You can also sign in with your email address without choosing a password. The default app that you fall on when you sign in is the Materials Explorer. All of the apps have little icons on this navigation bar. The Materials Explorer is right here. You can also access apps from this drop-down in the nav bar. There's the Materials Explorer. First, let's explore materials by chemistry. So for example, I can type in some elements, sodium dash oxygen. The dash means that I want all of these elements. Here I get a list of materials in a table. What I can also do is I can just click elements and that will select them. So say chrome and oxygen. And that will perform the search again. I can also go here to this mode selector and explore materials by formula. Here I can type in a chemical formula, for example, Fe2O3. We also get autocomplete for all of the reduced cell formulae that the Materials Project knows about. And this finds all of the polymorphs of Fe2O3 that we know about. There are advanced ways to search for materials, and you can look at this in the Advanced Search Syntax modal drop-down. It explains formula search syntax, and that you can use these asterisk wildcard characters to be placeholders for elements. You can also use this wildcard syntax when you're searching for chemical systems rather than formulae using the hyphen syntax. Let's try out a couple of examples. Let's say I want to search all binary oxides. I can type in an asterisk dash 0. Let's go back here and refill in that asterisk. I hit enter and I'll find all of these binary compounds that have oxygen in them. We can see here that it's only showing 500 of the most stable results out of more than 500. By stability we mean this energy above Hull parameter, which we'll explain in a later video. I can also use wildcards for formulae. So let's say I want to find AB2O3 compounds. I can have any element with one of them, another element with one of them, and O3. Notice that by typing it switched to the formula mode. And this search will find all AbO3 compounds. Great. Another advanced mode that we can use is by MP query. This uses a structured syntax that is the same as MongoDB syntax, which we use for our underlying database. And you can learn more about this syntax and all of the fields that we support at our documentation repository. So for example, quickly I'll go here, and there's a README here, but for example, I might type in that I want to search for ICSDs. I know about this inorganic crystal structure database, and I want to see if there are any tags by ICSDs. ICSD IDs. I see this, and I see what the response format is. So what I can do is I can take this field and I can use it. So for example, if I want to find ICSD ID 57958, and see if the materials project knows about that, I can enter in this empty query syntax, search, and I'll find this compound. Now we're going to explore by structure. So say that you have a structure that you want to search for. So we can go to this by structure thing, and we can drag a file. I happen to have this CIF file right here, and I can drag it there. It will search the database, and lo and behold, we find the structures in the database. Now let's explore by properties rather than chemistry. To do that, we can go to the sidebar on this right side. For example, band gap. Let me search between a range of band gap 0.5 EV, and it already reacted to that. And let's make this endpoint be 3 EV. So we see that our material list has filtered just by this property, not by chemistry at all. There are many results, and we only show the first 500 by stability by default. Let's also make sure that we only get the most stable results. So let's limit the E above hull to be 100 MeV, or 0.1 EV. Now we use a conjunction of band gap and energy above hull to filter these materials. Let's say we're also interested in materials that have a high quality band structure calculated. We can go to this has properties expandable widget, and we want electronic structure, band structure, density of states. We'll check that. And we also want materials that have full elastic tensor and properties calculated. That shrinks our list considerably. At this point, some of our properties have additional drop-downs. For example, for elasticity, let's say we want a particularly stiff material where our bulk modulus is at least 100 or so. And we get this great list right here. It's sorted by E above hull by default. We can sort by other fields by clicking on these arrows. Okay, let's do a little toy exercise now. Of AbO3 compounds with a band gap between 1 and 4 EV and energy above hull at most 50 MeV, which has the highest density in our database? We learned from our advanced search syntax, we have this wildcard syntax for those atoms with one of each in the reduced cell formula, O3. So let's get those. And then I want a band gap between 1 and 4 EV. And finally, I want an E above hull at most 50 MeV. So 0.05 there. And by default, we're going to get basic structure properties such as density. So let's sort by density. There we go. It's this hafnium lead oxide compound. Okay, now let's go over a material detail page. I'm going to type in here the formula of one of my favorite materials. Let's click on the row to open the page. Here at the top we have the materials reduced cell formula, its ID, a digital object identifier. We automatically generate DOIs for all of our materials so that they are individually citable. Down here we have an interactive 3D viewer. You can click and drag to rotate the picture. You can hold the Shift key and drag to zoom in and out. And you can hold the Option key and drag to rotate along the center axis. By default, we show the conventional standard structure type. You can also toggle the primitive type and a refined structure. Over here we have lattice parameters, and these lattice parameters are for the computed structure, which may not necessarily correspond to any of these process structure coordinates or the coordinates displayed in the image. Although they typically correspond to the primitive cell. Up here we have help guides. You can click this to toggle little inline help guides for a lot of our properties. In addition, we have more comprehensive documentation for all of our properties and calculation methods up in this documentation drop-down. The calculations guide is a good start. Up here at the top, we also have quick toggles to all of the various properties that this material happens to have. Not all materials have all of these properties. Let's go over a few of them. Here we have the electronic structure. We have a band structure plot and a density of states plot for this material. Note the warning. You can see our documentation for more information. You can also click down here to view interactive plots, which can be helpful. For example, we have projected density of states plots. Moving along, for many materials, we have a full phonon dispersion and vibrational properties calculated. We have a reference. We have these for many of our properties. And there are several additional properties you can download. You can also get interactive plots. This is similar to the crystal viewer up at top. You can click anywhere on this phonon dispersion plot to get the corresponding structure, the corresponding mode. You can also plot thermodynamic quantities as a function of temperature. For all structures, we have a computed X-ray diffraction plot. You can select a radiation source and you can download this data. For many materials, we have X-ray absorption spectra computed. Here's our reference. You can go to the documentation. You can click an element to display a spectrum average over all sites of that element in the structure. For example, to compare this with an experiment. You can apply Gaussian smoothing for better comparison with an experiment. And you can download these in convenient formats. For all of our materials, we have calculations for appropriate substrates for epitaxial growth. Here's a reference. You can choose any substrate orientation, and this is also available through our API, which we'll discuss in a subsequent lesson. Because this material has a full elastic tensor calculated, we can use the elastic energy for substrate selection. Here we have the elastic tensor. The stiffness tensor is displayed by default. You can also toggle to see the compliance tensor. And you can also visualize this with a third-party tool. We love linking to enthusiastic users of the materials project that want to contribute. We also have piezoelectric tensor here and dielectric properties in the tensor with links to reference and methodology in our documentation. We also occasionally have beta features. For example, we have this similar structures table which uses a dissimilarity metric, which is in progress and not finalized, using local environments. Finally, we have calculation summary for our structure optimization, and we have detailed input parameters and outputs for all of our calculations, and you can download those and look at them. This relaxes the structure. We have things for the band structure, density of states, etc. Here's another thing in beta, user contributions. This is, for example, a user that contributed band gaps computed using an alternate methodology to ours, and you can go to our MP-contrib site for that. Not all of you may see this as yet. We're rolling it out on a gradual basis. Finally, at the bottom, you can show the full provenance of this structure. For example, we obtained this structure from the ICSD, and then we ran our optimization on it. You can show how to cite this structure, etc. We also have links to external database IDs. For example, there are multiple entries in the ICSD for which this structure matches according to our structure matcher. And there are also some tags. If you have any questions about material, you can certainly go to our forum and ask a question about it, or you can ask the author. And there's lots more about how we make this over there. One thing I'd like to show you as well, a property that isn't on this page, we only have them calculated for elemental properties so far, would be surface properties. I'm going to go up here and go to gold, go to the most stable compound for gold that we have, MP81, and we can see up here surfaces. We have weighted surface energies and work functions for elemental materials right now, and for each surface slab that we use, we have these numbers as well. And you can toggle different views of the wolf shape that's constructed using all of these surface energies. Again, there's a beautiful periodic table of wolf shapes that you can go to visualize this a bit more. In addition, this material I noticed has equations of state. So we also have this available where we do calculations at multiple parameter tuples and fit them to various models. You can see a reference for this and download all the data in fits. Now I'd like to show you one of our other apps, the Battery Explorer. So I can say go up here and explore batteries. Let's say we're interested in all lithium-ion batteries. Let's go to the side here and filter by working ion, lithium. Okay, too many results. Let's refine our search. Let's search for cobalt oxide lithium-ion batteries. Here we go. This top one here, this intercalation battery, is very prevalent in cell phones and laptops. Let's go ahead and take a look at this. First, we have this discharge curve going from percent of lithium in this battery, and oxygen evolution, very important for safety. We have data on gravimetric capacity, volumetric capacity, volume change, energy density, specific energy. We also have a visualization for each of the stages of this battery. And here are the voltage pair properties. So each of these intermediate stages are materials in their own right. I could click on any of these and go to their material detail page. And in aggregate, they form this battery. And so that's how we produce a battery detail. Now let's look into another app we have, the Crystal Toolkit. Here you can enter material IDs or upload a structure and do fun stuff with it. In this case, I'll actually go back to the Materials Explorer, and I'll go to this material right here, and I will go ahead and click on Edit Crystal. That will load it directly into the Crystal Toolkit. And we can do a couple of things here at the moment. We can do supercell scaling, and we can do element substitution and removal by fraction. In this case, I'll simply substitute all of the oxygens with chlorine. And at this point, we can download the file and process it further in various formats. I would like to point out one thing. Let's download this as JSON. And take a look at what we give you here. So I'm going to open this. And what I'd like you to notice is it's stored as something that you can use PyMetGen with, our programming library, to do further analysis with. And also it's a transform structure, and we note all provenance. So for example, I can see here that what we did was a substitution of oxygen by chlorine. Here's our substitution transformation with our species map. And this will record everything that you've done to a structure. There's more functionality available in PyMetGen for this, but it helps you understand the provenance of your structures and how you made that new discovery. Another thing you can do is submit the structure if you think it's a new structure. Depending on our other priorities, you can check your dashboard, and we might compute a full structural relaxation of it and multiple other properties for the structure. And you can vote on other properties to be calculated, such as elastic tensor and soon band structure. Now I'd like to show you our structure predictor app. We can go here to the structure predictor, and you simply select up to 5 elements present, and you select valences. So for example, let's say I'm interested in predicting structures that have lithium, vanadium, phosphorus, and oxygen. I go down here, I inspect my valences. I'd like vanadium 3+, and yeah, that sounds good to me. And I'll go ahead and click Predict Structure. Now I'm not going to do this right now. Actually, I'll go ahead and do it right now. So what this will do is it will queue the calculation on our end, and when you go to your dashboard, you can view the progress of all of your past calculations. You can also access your dashboard at any time up here. And I've actually already run this calculation, so I'll go up here to the result, and we can see this result. All results are private by default. You can make it public so that anyone can view this with that URL. And we have a bunch of candidate structures using our ion substitution algorithm, where we data mined the ICSD database of experimental structures to determine likelihoods of substitution probabilities. So these are all derived from other compounds. For example, let's go to this candidate structure, and we can see it's based on the structure with this ICSD ID. You can download all of the structures or VASP files if you'd like to run simulations on all of them. Now let's explore the phase diagram app. Experimentalists unsuccessfully attempt to prepare the ternary phase NAFES2. Let's use the phase diagram app to map out the stable phases of the sodium, iron, sulfur chemical system. Using the lever rule, we can see what any composition might decompose to. For example, let me go ahead and plot out NAFES2. So these elements in a 1-1-2 composition. So that would be right here. So we'd expect, actually, if we tried to synthesize this compound, it would decompose to these stable compounds. Okay. We can also just search for that composition in the Materials Explorer. And we can see in the material details, this decomposes to field, where it will decompose to these materials. Now, going back to the phase diagram, we can use other functionality here. For example, we can make one element open to the environment. The effective temperature and partial pressure can be captured in a single chemical potential variable with a more negative value corresponding to higher temperatures or lower partial pressures. These are grand potential phase diagrams. So let's say we were in an environment that was open to sulfur. We can vary the partial pressure and see that the stable phases change. Now we're going to look at the POURBAIX diagram app. With the POURBAIX diagram, it's similar to a phase diagram, but you can examine the aqueous stability of a compound, so with the presence of oxygen and hydrogen ions. So let's examine the potential diagram, the POURBAIX diagram, for the 50% 50% bismuth vanadium system in aqueous solution. (50% 50%), which we could toggle with this. And let's ensure that both ion concentrations are at 10 to the minus 5 moles per kilogram. Now, is bismuth vanadate, BiVO4, expected to be thermodynamically stable against decomposition at potentials close to the oxygen evolution potential? Here's the oxygen evolution potential. And here's bismuth vanadate. So actually we see that it's not expected to be stable because this blue region indicates a stable solid compound. You can read more about this in the documentation up at top. What we can also do is for any material, we can generate a phase diagram. For a compositional phase diagram, it simply uses the elements in the material, but for the aqueous stability diagram, it does something special. It adjusts the concentrations relative to the material, but it also produces this Gibbs free energy map, where you can see essentially a heat map of the Gibbs free energy of your compound with respect to the POURBAIX stable phases, where you can see blue is perfectly stable and red is unstable, greater than 1 eV per atom above the hull. And beyond that, it's too large to consider. Let's briefly walk through our reaction calculator app, where you can determine the energies of solid-state reactions using our database of calculations, as well as compare to experimental values when available. For example, let's search for this reaction to form calcium carbonate plus CO2 giving calcium carbonate. We can see this theoretical value calculated, and we don't have any experimental value on hand. However, let's now try this reaction with Al2O3 to produce MgAl2O4. For this reaction, we do have experimental data, experimental value with which to compare our DFT produced value. You can see it's comparable. And you can see experimental references as well as go to our individual compounds. Now let's look at the Molecules Explorer. We're skipping over a couple of apps like simply comparing element data and nanoporous materials. With exploring molecules, we can explore by elements as well as a bunch of properties along the sidebar, and you can also search by substructure. Let's do that. Here I will draw a pyrazine ring, and let's flank it by a couple of benzene rings and include that substructure, and we find a bunch of molecules that use that. I'll examine the one with the highest ionization energy or ionization potential, and we can see that we can get a visualization, download the XYZ coordinates, and get a bit of computed data on that. In addition, for all of our results, we can explore solubility in an aqueous or non-aqueous redox flow battery. So we have this whole dashboard right here, and we did this via the Molecule Explorer. You can also import molecules via CSV, adjust battery price target, and all these other parameters and operating conditions. Okay, now let's look at X-ray absorption spectra. We have this XAS Matcher app up here, And you can browse. So for example, let's enter a chemical system, lithium cobalt oxide, and an absorbing element. Let's look at oxygen. So we have 28 materials in this chemical space with computed spectra for oxygen. You can plot computed spectra, compare them. Let's see, you can plot these two as well. And we can go to those materials. And we can download all this spectrum data. You can also use Gaussian smoothing. Another feature is you can upload an experimental spectrum that you have and compare it with our database. So I went to the EELS database and I found a great aluminum alpha spectrum, an aluminum K-edge. So these are all Zane's K-edge spectra. And I have in their format. Let's open it up. You can inspect it and use our matcher to find matches. And this in fact was this compound, Al2O3. So there are a bunch of polymorphs that are very close, and we can determine which one looks a little better. So here's the uploaded spectrum, and here are these other ones. There are certain shifts applied, and you can use smoothing, but this can be a helpful tool. Now let's look at another one of our apps, the NANOPOROUS Explorer. This is a giant database of over 500,000 nanoporous material structures. This app is disconnected from all of the other apps, so these aren't our organic crystal structures. This is kind of an isolated database, but provides a useful tool for exploring the structure and absorption properties of nanoporous materials, where the data is provided by this Nanoporous Materials Genome Center, all simulated data. You can select a sorbent material and a sorbate. Let's explore. Let's also go ahead to the sidebar here and make sure that our materials have isotherm data. And we have this big graph here, and we have x-axis and y-axis. We can toggle these to plot different parameters. And we can also zoom in. So this isn't showing all the data because we have so much data. We can say, go on this graph here, and you can see only a few data points here, but if I click and drag to zoom in here, it will requery in that parameter set of void fraction and crystal density range in this case, and it will produce a table of all the records within that filter. Let's go to one of them, and we can see this nanoporous material. We have a structure for it, a few material characteristics, and some absorption properties, methane heat of absorption, absorption isotherm, Henry's coefficient. You can find more about this from the Nanoporous Materials Genome Center. Another quick little app we have is comparing elements. Here we just compile experimental data on the elements. So say you can load up iron and chromium and another element if you wish, and compare basic data that we have compiled. This is all available in PyMetGen properties as well. These are not computed properties. So if you want to get a quick sense of trends, you can use that. We also have a small collection of experimental thermodynamic data compiled from external sources. Here you search by chemical composition, not by elements or chemical system. So let's look up Fe2O3. and we can see a bunch of data that you can compile and put together at your will. You can see a legend up here that places all of these various coefficients in their context, and these rows corresponding to each of these coefficient values for given temperature ranges. Now, a little bit on how to find help. At the bottom of all of our pages, we have a link to our discussion forum. This is very active. Many of the Materials Project team members subscribe to this and try to answer things, and we hope as active members of the Materials Project community you will help out as well. You can also find out more about our project, some stats on what we have. If you collaborate with us and with any of our code repositories, you'll get your name up here because you're part of making this happen as well. If you'd like to cite anything, I went to that citing link at the bottom. There's this general link, but also for each of our various facets of the website, we have individual citations for all of the work that went into that. And so we suggest that you cite those references as well. Terms of use is important. Generally, this data is here for you, but if you plan to download large data sets, email us so that we can avoid flagging your account as abusing the service, and we might also suggest an efficient way for you to obtain the data that you need.